So I'm going to walk through the program and then also the lab report results. So first, let's do the 2 to the 16 for the delay count. So let's compile it and run it on the MSP 432. Okay, so if I run it, you can see that it's blinking about every half second is what I measured. So now let's around a fourth to a half of a second, roughly. So now if we look at 2 to the 18, save that, debug, and once that's done, you can run that. And the measured time for this one was roughly 1 second per blink for 2 to the 18 for the delay count. And now let's do the following count. So I'm just going to go through each one. Okay, now we have roughly 2 seconds for each count is what I measured for this for 2 to the 19. 2 to the 20. Okay, 2 to 20 for this one. I measured roughly 4 seconds. And now we can do the last two. So this is 2 to the 21. And for that one, I measured roughly 8 seconds per blink, so pretty slow comparatively. So every time n increases by 1, it doubles in length, pretty much. And now finally, 2 to the 22. So this one will take around 16 seconds per cycle, the blink cycle. It's pretty slow. And it's currently running, just waiting for it to blink. There you go. So that was roughly 16 seconds. So I can stop that. This will continue. So now looking at the lab report results, I plotted each of these delay counts, starting from 2 to the 18 to 2 to the 22. I plotted it linearly. It's exponential, but I did it in a linear manner. So it's easier to see the relationship, the doubling relationship per increase. So So yeah, it starts off at 1 second to 2 to the 18, and then just doubles every time you increase n with 2 to the n relationship. And yeah, so if the delay is such as t25, it's the LED doesn't blink, just stays on. And breakpoints, you can set breakpoints just by double clicking on the sidebar or by right clicking and toggling it on the sidebar. Sometimes breakpoints aren't allowed or they are disabled automatically. Like if you do one on a line that doesn't have any code on it or a line with a comment, or if a state change doesn't occur, the breakpoint doesn't toggle. And they're used for just debugging purposes to see like system state of the program at that particular instance and that step of the program, variables, things in memory, and such. Now looking at the assembly code. So for the assembly code, looking at, this is the main function represented in assembly. And if I scroll down, I see this is the while loop, the infinite while loop for the program. And then this loop only exists on one line. It's the for loop. That's used for the delay count. So this is the assembly code for the for loop for the delay count. I counted 16 lines of 16 instructions in here roughly. So doing some math, I calculated that the frequency of the MSP42 was roughly 4.19 megahertz. The operating frequency based on how many seconds each delay was and the energy value of the delay count, and knowing that each instruction, one instruction was executed per clock cycle. So I just did a simple conversion to frequency, and then using that frequency, if you want to define the delay count for a 12-second on-off cycle, you just have to substitute in the frequency and then solve for delay, given the same amount of instructions, and then given 12 seconds for the period of time. And looking at the binary executable files that were outputted from the debug mode and the release mode, it's shown that the debug executable file is actually larger than the release executable. And this is because the release executable is better optimized and it cuts out some of the code needed for debugging. And yeah, that's my report.